Hello, everybody. I'd like to welcome you to the third webinar on powder rheology. My name is Timothy Ashel, and I will be presenting you this webinar on powder and air, what happens when powders and granular media are fluidized, and how that impacts their behavior. We will start with a brief introduction today on powders, on their behavior, and what fluidization is. The next point will be how powders can be classified regarding their fluidization properties. And the final part will explain first the setup of powder rheology with a rheometer, and then we'll see some measuring principles as well as some applications for these measuring principles. Let's start with introduction. When you're processing powders or handling powders, they can show quite a complex behavior depending on what you're doing. Different questions and challenges might arise. If, for example, you're pneumatically conveying your powders, then you might wonder which form of transport is possible. For example, dense phase flow or dilute phase flow. You might also want to know what airflow is necessary for pneumatic transport. The powder is flowing through a nozzle, then the nozzle design and thereby the shear rate will impact quite strongly how the powder behaves during the spraying process. Another example might be, for example, to look at fluidized bed reactors, where the fluidization properties can quite strongly influence as well how the powder behaves in the fluidized bed reactors. Then one last example that I'd like to give you before we start off with influences and powder behavior is discharge of a silo, because this is actually a bit something that is counterintuitive because we don't really see an air that is forced through a powder. But when the powder is in free fall, it actually fluidizes by itself during this discharge process and can also impact the powder behavior either during the discharge but as well afterwards. So with this, let's have a look at powder behavior. Powder behavior can be quite complex, and it depends on many different internal and external influences. Among the internal influences which strongly impact the fluidization are, for example, particle size and size distribution, as well as the density. If we look more towards external influences, there are quite a lot of different influences as well, but specifically towards fluidization, we might want to have a look at humidity, gas flow rates, and of course also if the powders were pre-consolidated. These internal and external influences change the powder behavior. So they will impact, for example, how the powders flow, how they can be compressed. But in this webinar, we will focus on the fluidization properties and how to measure them. Before going into fluidization properties, we have to talk or have a look at what it means to fluidize powders. So in fluidization, pressurized gas is introduced through the powder bed. If the gas flow is strong enough, the gravity and interparticle forces are overcome, which results in a dynamic fluid-like behavior. We can see on the right side a video showing us an example where the air is flowing through the powder from the bottom of the cell. You can see here on the bottom. And this fluidizes the powder. So we can see here also that with a strong enough airflow, the powder even starts to bubble and spout like if a liquid is boiling. There are quite a lot of different applications where powders are fluidized on purpose or they are fluidized just by the process they undergo. Let's first look at pneumatic conveying. Here powders are transported through pipes with pressurized air or pressurized gases. And generally there are two phase flows that are differentiated, for example, dilute and dense phase flow. Dilute phase flow, here high gas velocities at low pressures are used, and the material is generally kept in suspension, so it shouldn't accumulate in the conveying line. In dense phase flow, on the other hand, we're having more of low velocities and high pressures, so often the material is transported as a plug through the system. So next we'll have a look at fluidized bed processing. When we're looking at fluidized bed reactors, these are generally used, for example, in petroleum industry for fluidized bed catalytic cracking. These fluidized bed reactors are usually used to process materials to ease or improve catalytic processes, chemical processes. They have the advantage of a very uniform particle mixing and also a uniform temperature gradient in the powder bed. Another example of fluidized bed processing is the granulation, which is often used in pharmaceutical industry, but can also be drying of powders, coating of powder particles, and so on. But fluidization often takes place also during processing. So if we're looking at free-falling powders. So this would be a gravity-assisted fluidization that can take place, for example, during discharge from silos and hoppers, but can also happen when a rat hole collapses. So this can result in uncontrollable discharge, and it's something we'd rather be sure to know what's happening. What might change as well, and what is interesting if you're looking at filling of bins and containers, is that the bulk density might change drastically as the sample takes in the air and retains the air for a certain time. So this might also influence negatively downstream processing of the powders. This leads us to the next part, how powders are classified. Powders can be classified in many different ways. It's possible to classify either by product variables or by product characteristics. Variables look more at certain properties, like particle size or size distribution. You might look at the morphology. And then we have the classification by product characteristics, where we're looking at the behavior of the powders. So do they flow well? How do they behave during consolidation? And another way to look at it is also how do they fluidize? And for this, we look to Derek Geldart, who was a researcher for fluidized bed technology and did fundamental research in this field. In his PhD thesis, he published a way of classifying powders by their fluidization behavior. For this, he looked at the relation between the particle size and the density difference of the particles and the gas which is used for fluidization. With this, he classified the powders into 4 groups of different behavior. The resulting publication in 1973 is still one of the most cited works in the field of powder and granular media. Now, if we look at this in a bit more detail, we can see these 4 groups here on the right side. We have the groups A, B, C, and D. The group A are aeratable powders, so powders that can be fluidized relatively easily and nicely, rather small particle size with about 100 to 200 microns, with a relatively low particle density, lower than 1.4 grams per cubic centimeter. And when these powders are fluidized, they show a strong increase in the powder bed height, and they also show a very large or good air holding capacity, which means that the air remains quite long in the sample once it has been fluidized. On the other hand, they show a very low gas permeability, so it's difficult for gas to pass through the sample. An example for this might be aluminum. In group B, we're talking about sand-like behavior. So again, we have a particle size of about 40 to 500 microns, with the particle density as stated here, 1.4 to 4.5 grams per cubic centimeter. When these powders are fluidized, they will show a relatively slow increase in bed height and a less pronounced increase in bed height as before. They have a medium air holding capacity or air retention, so the air that remains in the sample for a while is less than for the group A, but they have a higher permeability than the group A shows. If we look at the group C, which is at the bottom left of this graph, we can see the cohesive particles. Here we're talking about very small particles usually, which are very cohesive. When these powders are fluidized, or when we try to fluidize these powders, the powder lifts generally as a plug, or it will develop some channels. So these powders are difficult to fluidize, but this can also be improved by, for example, stirring the sample or mechanically agitating the sample. An example for group C is would be flour. In the group D, we're talking about spoutable powders. So here there are very large particles, um, larger than 600 microns. Here, large gas velocities are necessary for the fluidization, and it's already quite difficult to fluidize these. And these powders also show rather low air holding capacity, so rather low air retention, and they also show a low gas permeability. Example for this would be rice, for example. Another way to look at this is the cohesiveness. So we can differ between cohesive powders like group C and non-cohesive powders. And cohesive powders will rather stick together tightly, and they will be difficult to fluidize. This means when we fluidize them, they either move as a plug, or we might see some channels that are that build up in the powder bed. As you can see here, there's a channel where the air passes through the powder bed, but stirring them can improve the fluidization. If we look at non-cohesive powders, the particles do not stick together as much when they are fluidized. They separate nicely, and these powders or these granular media are rather easy to fluidize, and are generally also easy flowing or free flowing. This brings us to fluidization measurements, where we'll start with the setup and a brief introduction to measurements as well. So let's first start with the measurements. Much research has been done on powders. However, empirical methods, as we can see here on this slide, are still performed in many companies around the world because they're simple, they are easy to carry out, but they're not always close to the application, so not always describe the application very well. There are measurement methods that are very similar to methods that were used or still are used in traditional rheology. So you let a liquid run down an incline and measure the time. This is something that is also done more or less for powders with, for example, the Hall flow meter, where the powder runs through a funnel and the time is measured that the powder needs to run through it completely. One thing that should be mentioned is that this, for example, is a measurement that is quite operator dependent. So depending on how the funnel is filled, the powder, of course, will have a certain state of pre-compaction, and so it will flow differently. Another method is, for example, to tap the powder and look at the tapped density, so look at the density before and after tapping and put that into relation, which will also give some information on flowability. There is not so much that exists for fluidization experiments from these rather empirical methods. Anyway, what we can still say is that these measurements are usually only comparative, so not absolute measurements, as well as the reproducibility often depends on the operator, or sometimes not even that, they're just not very reproducible. There are also some more advanced methods regarding powders. So for example, cohesion tests, like a Warren spring test or penetration tests. When we're talking more about fluidized powders, we'll more look at Sevilla testers or, for example, powder testing with Anton-Barr powder cell, where we can control very precisely the airflow and measure the pressure, be quite precise on what is happening in the powder while it's fluidized. So this brings us to the setup. And this is what the setup of the powder cell and the rheometer looks like. We have on the bottom, we have the measuring cell holder, in which the measuring cell with the measuring tube can be inserted very simply. It's just a drop in and twist until it clicks. So this is very easy to remove and to exchange for samples. And on top of this, we can also see the patented dust protection hood, which keeps the powders in the cell even when fluidizing. So this is very practical because even when you're fluidizing the powders and they're showing this dynamic fluid-like behavior, they will remain in the cell. The gas flow into the cell is introduced in the bottom of the cell. So there's a porous glass frit in the cell at the bottom, and through this glass frit, the gas flow is introduced. Generally, um, this is done just with normal air, filtered air, but this can also be done with pretty much any gas you want to. So if you would rather use argon or nitrogen, that's easy. It's just the mass flow controller that controls the airflow that has to be adjusted a bit. If we look at this explosion diagram, we can see there is in the back the mass flow controller, which can control the airflows from very, very low flow rates, so starting at 0.05. And depending on the mass flow controller which is used, it's possible to go up to 80 liters per minute, so quite a large range as well. For powders that are easy to fluidize, like metal powders that are used for additive manufacturing or polymer powders that are used for additive manufacturing, you will rather go with a very small one. So it'll be in a range of 0.05 to 5 liters per minute. If you want to fluidize more cohesive samples like cement or gypsum, then you'll rather use the largest one, which goes from 1 to 80 liters per minute. We can also see this sealing air, which is attached to the dust protection hood. So this dust protection hood has multiple parts in it to keep the powders inside. One is a sealing air that is pumped into the system, which keeps the powders from leaving via the open shaft, where the shaft of the measurement geometry goes to the rheometer motor. And there are also other filter systems inside to keep the powders in. Also quite interesting probably here is the pressure sensor, which is attached on the bottom of the cell, which allows to measure the pressure at the bottom of the powder bed. We will also see with the measurements that we will be looking at, we will see why this is interesting. So with this setup, it's possible to look at powders in different states. It's possible to look at powders in a compacted state. It's possible to look at powders in a deaerated state, but it's also possible to look at powders in fluidized states. And with all these states, it's possible to look at different dynamic and static properties and characteristics of powders. Specifically for the fluidized state, we can look at fluidization properties. We can look at fluidized bed viscosity. It's possible to look at the air retention capacity of powders. And it's also possible to measure the tensile strength. And this brings us to the measuring principles. So today in this webinar, we will be seeing a bit about the pressure drop, as well as the deaeration and air retention. And we will also have a look at some applications in this area. For the flow curves and tensile strength, these two methods will be treated in further webinars, as we are a bit limited in time today. So let's start with the pressure drop. The pressure drop is generally used to either determine the volumetric flow, so the gas flow for full fluidization or incipient fluidization, but this is also to find out the airflow necessary for sample preparation, because if a powder is fully fluidized, it's possible to erase the powder memory. So the intrinsic stresses that are on the powder by filling the powder into the powder cell and so on, these can be removed by fully fluidizing a powder. And so this can be very practical if you want to carry out different tests. For example, if you want to measure the cohesion strength, so look at the flowability, it's very practical to fluidize the powders beforehand, because like this you can remove these intrinsic stresses and you get reproducible results. So now let's look exactly how this is measured. This measurement is carried out by basically two intervals. In the first interval, the volumetric flow rate starts at relatively high values and it moves downwards, so we decrease the volumetric airflow. So this is the red curve. So in this case, we'll start at 2 liters per minute and we'll continuously decrease the airflow down to 0.05 liters per minute. And we can already see this quite interesting. What we're measuring here is the pressure And already on the downwards flow, what we can observe is that the pressure remains more or less constant, and then starts to drop and then show again a constant decrease here at the end. Once the airflow is stopped and we start again from 0.15 liters, or 0.05 actually in this case, start 0.5 liters, and we increase the airflow, we'll first see a constant increase in the pressure curve. And in this part here, the powder is not fluidized yet. So in this case, up to about 0.42, 0.43 liters, the powder is not fluidized, it remains static. And at the point where we can see this overshoot, this drop in pressure, the powder starts to fluidize. So we can observe this as the point of incipient fluidization. When the gas flow is further increased, this pressure curve becomes more or less constant. And at the point where it becomes constant, we can see that this is the point of full fluidization. So we can see here, okay, at what point does it start to fluidize, and at what flow rate is it fully fluidized. One example for this is powder coating. So in powder coating, there's a material that's used for coating, for example, car parts, and this is in a fluidized bed. So here we have a fluidized bed. We can see this on the bottom, where the particles are always kept in suspension, and then they are removed and transported pneumatically to the nozzle. And so if we look at this, here we have two different samples. One is with a flow additive, so with aerosol, this is the gray one, and we have the red one, which is the same sample, but without flow additives. So we're wondering, how does this flow additive impact the fluidization properties? If we look first at the powder coating without the flow additive, we can see that it fluidizes, or it starts to fluidize at about 0.26 liters per minute. And if we add the fluidization, the flow additive, we can see that this overshoot, it moves quite a lot to the left. And we're now at 0.16 liters per minute for the starting fluidization. So we can see that this is a relatively strong decrease. So this improves the fluidization, which means that the air which is necessary to run this fluidized bed reactor is less if we're using aerosol than if we're not using the flow additive. This means we can actually save money by adding the flow additive, because this improves the fluidization behavior. So now we'll have a look at the next measurement method, which is deaeration. Here, what we do is we pass air through the sample, which increases the bed height, as we already discussed or saw before. And then at the point 0 in this interval time, we turn off the airflow and we measure the pressure under the powder bed. So we will see, as the pressure decreases, we'll see different kinds of decrease. We'll first see a very rapid decrease, which is followed by a more slower one. And then at some point, the pressure becomes constant. And so this point where it stops to decrease, where the pressure becomes constant, this point shows us where the powder is deaerated. So in this case, if we look at the red sample, it is deaerated after about 2 seconds, while the gray sample is deaerated after about 13 seconds. The deaeration can be interesting, for example, when pneumatically transporting powders or bulk solids. But this can also be interesting to evaluate the transport for abrasive or friable material, or improve the energy efficiency of pneumatic transport. But this can also be very interesting if you are, for example, filling samples that have a very high air retention capacity, because this will indicate you that you might have to wait 12 seconds before continuing filling. So we'll fill it in the first step until it is full, wait 12 seconds, and then continue filling. An example that is here in this case pneumatic transport is again the powder coating. And in this case, we again have the two powder coating samples, red without flow additive and gray with flow additive. And we're looking at the step after the fluidized bed, where we remove the powder out of the fluidized bed and we transport it pneumatically towards the nozzle, where it is then sprayed on, for example, car parts. If we look at this, so before measuring the powder is fully fluidized, we turn off the airflow and we measure the pressure after the airflow is turned off. So we can again see here in the red curve this very quick decrease of pressure, followed by a rather slow step. And we can see that the deaeration is more or less completed after 4 to 4.5 seconds. So without flow additive, it takes about 4 to 4.5 seconds for the powder to fully deaerate. If we add the flow additive, on the other hand, we can observe quite similar behavior in how the curves behave, in the sense that we first see a very quick decrease followed by a rather slow decrease of pressure. But in this case, it takes about 9 seconds for the powder to deaerate. So this means we have an air holding capacity of about 9 seconds, so about double the time than without the flow additive. And this shows us that the air holding capacity is quite strongly increased with the flow additive aerosol, which actually will improve the pneumatic transport in the dilute phase flow. There are also other fluidization measurements and applications. So one is flow curves. This will be also discussed in further webinars. Flow curves are basically fluidized bed viscosity, where the apparent powder viscosity is measured in dependence of two factors, the shear rate that is applied and the fluidization rate. So it's measured in fluidized and subfluidized state, for example, with a shear rate variation. Another measurement method that can be carried out is the tensile strength, where the powder is fluidized to measure the interparticle bonding forces. And another one where air is used is the permeability, where the resistance towards airflow of a powder is measured. The applications, what we are interested in this, also include, for example, to clear the powder memory by fluidization as a sample preparation mode, which can lead to high reproducibility for a lot of different measurements, like, for example, the cohesion strength. So in the cohesion strength, the powder is first fully fluidized before the measurement is carried out, in order to remove intrinsic influences by the powder, by the operator, by the filling, and so on. Another application which can be carried out with this is foam stability. So the foams will actually be created in the powder cell by adding some liquids, for example, water and tensides, and foaming it in the powder cell directly and measuring how long, or the torque. And by this, it's possible to look at how stable the foams are over time. With this, I'd actually like to finish this presentation and this webinar. If you have questions, please feel free to write to rheoapplication@antonpar.com. And thank you very much for your attention, and I hope you will listen to all our other webinars. Thank you.